Welcome to today's webinar. The topic today is how to consider masonry in Rfem 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, webinars, the technical content of the website, customer projects, newsletters, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Ulrich Lex will be the presenter today. He's responsible for the add-ons masonry design, glass design, construction stages analysis, and he works also in the customer support team. Okay, I say some words how you can ask questions, at least for the attendees who participate the first time. I switch off my webcam that you can see the full screen. If you have a question, just press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Ulrich. Ulrich, it's your turn.
Thank you very much, Andreas, for your introduction. From my side, hello to all to today's webinar. The topic of today's webinar is masonry, what we have implemented in Rfem and how we could use it for the different situations. The webinar is separated in three parts. In the first part, a few words to the material and the material parameters. The second part is about the differences of the material models, of the implemented material models in Rfem. And as the last part, some examples in Rfem 6. Let us start with the material parameters. The material masonry is a quite difficult material because it's not only one material, it's a mix between bricks and mortar. It's a combination of two different materials. Therefore, there are a few possibilities how it could considered in an FE program. The most detailed possibility would be a detailed micro model. This detailed micro model would mean that the stones, or the bricks and the mortar are directly created in the Rfem model. So each brick is one element and also the mortar joint is an element too. That would mean that the individual components are exactly created in the program. But the disadvantage of this option would be that you would need a lot of input, a lot of time to create this. You would have a lot of calculation time. So I think it's not sensible to compute with this detailed micro model for a big building or something. A second part would be, it's called simplified micromodeling. Here it's a little bit easier. The combination of bricks and mortar is created in this way that only one element is created for a brick, and between the different bricks or blocks are contact conditions defined. I could imagine that it would be possible in Rfem to create such a system with surfaces in combination with line releases, or maybe even with solids and contact elements. The third and more easy modeling would be a macro modeling. Here you will create the masonry as one surface, and the material models, the material parameters between the bricks and the mortar are smashed above the whole surface. So this means the modeling is more easy, and it's faster than the other two options. One small disadvantage is that maybe if there is anywhere a crack in the masonry wall, you could not define exactly the location in maybe the mortar joint because the parameters are smeared above the whole surface. But this macro modeling is what we use in Rfem. So what do we need for material parameters in Rfem? For the first step, for computing the internal forces, we only need the modules of elasticity and the shear module. This is everything we need for the first step. So how could we get an idea about this elastic modules and shear modules? Here we find an answer in the Eurocode. The determination of E modules is defined by one factor. It's about 1000 for clay. It's in a range of 800 to 1250 for calcium silicate, or maybe 2050 and 2700 for manufactured stones. This multiplied with the FK, characteristic strength, is the E module. For small stones, for historic stones, you can add an factor where reduction of the E module, a small reduction of the E module, according to the height of the brick and reference height. The shear module is quite easy because this is 40% of the E modules in this direction. So this is all for the first part, and here I want to change to switch to the program. So as before I start to modeling something, I want to check if in the add-ons in the base data my masonry design is checked on, because this is the most important thing if I want to work with masonry. Today I prepared a small example. It's one wall with a slab and a defined load above. So I want to show the differences between the material models. That's why I have created some materials, and I want to show you the differences now. As the first material is the material with the isotropic linear elastic material model. This isotropic linear elastic material model is our basic material model. It's the same for concrete or steel surfaces. You only need one E-module, elasticity module, and shear module to compute the internal forces. When you have chosen the material type masonry, then you have here the possibility to create also an isotropic masonry plastic surface material model. This means the isotropic option is that we have one E-module for both directions. In X and Y direction, we have only one module of elasticity. But with this plastic option, you can say that the limit stress for tension is reduced, because masonry cannot handle any stresses for tension. There always will be the wall will be cracked if tension is, and the difference to the first material model, here also a tension is in tension can be computed. In this plastic isotropic plastic material model not. Here you have the possibility to cut a limit of tension. But be careful, directly insert 0 is not good, because the calculation will be not good for a value of 0. So you have to insert a small value. So the third option is the orthotropic, and this, I would say, it's the most exact material model for masonry, because here we have a different module of elasticity for the Y direction, for the strong direction, and the X direction, I would say the weak direction of the bricks, and a shear module is considered too. Additionally, you can limit not only the tensile strength, we have also a limit of the compressive strength, and these allowable values from tensile and compressive strengths are computed according to the Eurocode. That would be mean again, if the calculation with this material model is done, then the design of this wall is done too. So these three different material models we have in Rfem. As a last option, we have one type of thickness. We called it shear-free. You can choose it in the thickness type wall shear-free. That means if you choose this thickness type, that this wall can only transfer vertical loads from the top to the bottom, but no shear loads shear loads of the system. So I will show you later where you can use this thickness type. Okay, to our system. Here I created one masonry wall with a slab, and I want to assign this different. I want to create one more walls with copy. Maybe this direction and copy the loading too. 1, 2, 3 times. Okay. So in the first wall I have to assign the isotropic material. In the second wall I want to consider the thickness with the isotropic masonry plastic. In the third case, I want to consider the orthotropic masonry plastic. And in the fourth part, I want to consider here my shear wall thickness type. For the shear wall thickness type and the horizontal load, I need some additional elements. That's why I added here 2 beams, 2 members as a column. Section from concrete. Okay, maybe for this case. So now I have defined on the first step the isotropic material model, the isotropic masonry, the orthotropic masonry, and in the last step the shear-free wall. So I want to take a look on the easiest load, on the vertical load. A short look into the mesh settings. I have a mesh length about 250 centimeters, and this is the value you have to use for masonry. Okay, now I can compute this first load case. So when we take a look on the results, I want to look at the stresses, and here I have something like the load trajectories, where you can see how the load is transferred in the surface. And we see for our first isotropic system that the load is transferred above the whole length of the wall. This is not as expected because we would think that the load is in an angle of 60 degrees transferred, and the other parts of the surface did not get any force. But for the basic isotropic linear elastic material model, it's not as expected for masonry systems. When we take a look on the second system, it's better. Here we have no tension force in the system, and therefore I have not such a big transferring to the sides. You see on the support reactions that the load is transferred in some angle from the top to the downside. When we take a look on the orthotropic system, then you can see it's better than the other two. It's more homogeneous, and it's transferred like expected. In the last part, you will see that there is no there are only vertical loads in the system because of the members on the side. You have an homogeneous transferring from the top to the bottom, but you have only straight loads in the system. It will be more clear when we have this horizontal load in the system too. So when we add this horizontal load, then I want to take a look on the load combination, because in case of a horizontal load, you always need a vertical load, maybe self-weight or an additional vertical load too, because masonry cannot, because of the fact that masonry cannot handle tension forces, you can not compute only horizontal loads on the system. For this calculation, I have to modify the support conditions. I have to fix it in X direction. Okay. And now I can compute this load case again. Here we can again, we see again that the load transferring of the internal force of our isotropic system is not as expected. Is not as expected in the system. Here I can change it one time more, then it's more clear. I can deactivate the nonlinearity, so we can see also the tension in the system when we compute it again. Now you can see that in this isotropic material model, also tension forces are inside the surface, and therefore the load transferring is not as masonry works. So in our isotropic material model, it's quite better. You see that this horizontal load comes into the surface and it's transferred in this direction to the bottom of the surface. It's like expected, but because of the fact that we have only an isotropic system, so the E module in both directions is the same, and this exact shear behavior of the masonry is not so good considered with this material model. The most exact system is the orthotropic one. Here you can see that only tension is like it's defined in the material, and the pressure is transferred in the right way to the supports. In the last option, you will see that the masonry wall get no horizontal loads. There are only vertical trajectories in the system. Here also we can take a look at the internal forces. We only have vertical loads Ny in the system. This horizontal load has to be here has to be something created for this horizontal load. That's why I added this concrete columns. You see here is a moment in this member, because this surface cannot handle shear forces. Okay, this one was the explanation of the different material models, and on this part I want to switch to the second example, to a small building where we can create now the masonry walls and to compute this. So I have created some building, 2 floors with concrete slabs. In the front, some columns in concrete, and in the back I want to consider masonry walls. Therefore I defined some materials. One, the isotropic masonry material models for the surfaces who should acting for shear forces, and for the walls inside the building, I do not want to consider shear. There I have to create the isotropic material model and want to use the thickness type wall shear free. So when this is defined, I can continue with creating the surfaces. I use the option boundary lines. I choose my thickness. Okay, and create and create the walls. So it's quite easy when the lines are there. And the last one. Okay, for the inner walls, I want to use the thickness shear free and create here my inner walls. So, and upside, I have here one wall. Here I see there is no column. I want to add it here as this member with the section in concrete. And also a curved surface is no problem, but I have to use the quadrangle surface. One, two, three, and four. So then all walls are created. On these surfaces, I want to add a window, maybe an opening. Here also I can use the option graphically and select only my lines. The opening will be created automatically. On this part, it's important for masonry that when we have some big openings, we always have to assign something like a lintel above the opening, only because of the fact that the masonry cannot transfer or cannot handle tension forces. And if here acting a big load is assigned, or if the opening is too big, then there would be here a lot of tension forces, and this would lead to an instability of the calculation, because the wall cannot handle tension forces, and they could not be transferred to the side. That's why we have here to add something like a lintel. I assign a member and create here a new section, maybe with concrete, with the width of the wall, and the height maybe 10 centimeters. Okay. For bigger openings, it would be good to create it inside the wall a little bit, so that the load is not transferred on one F image here. But in this case, it's okay in this way too. Okay. Then as a next step, I want to take a look. I want to select all my masonry walls. I want to take a look on the axis systems, because it's better for interpreting the results when the local x direction or the local axis system is oriented in the same direction. Maybe local z goes outside of the building. Therefore, I have to reserve this, and here. Then I can say, when I take maybe a look on the stresses, that all stresses with positive sigma x positive is outside of the surface, and sigma x negative is inside of the surface. Here it's okay. This wall is orientated in the different way. And then it's okay. As a next step, I want to take a look on the FE mesh settings. Here globally 0.5 meters assigned. It's okay for the concrete elements, I would say, but for the masonry I would use finer mesh. Therefore I can select all surfaces, edit, and assign mesh refinement. I can create a new one, 0.25 millimeters. Okay, and I want to check it. If it's I would say a nice FE mesh is created, or if I have to refine it in another part, but it looks good on the steps, then everything is okay. So then I think we have finished the modeling. Then we can take a look on the loading. I want to deactivate the local, so we can take a look at the loading. I have created a load case for the self weight, for the imposed load, a snow load on the top, and I want to design some wind load in one direction. Here in global X direction. Here I can create a new additional surface. Again, I can select the boundary and use the stiffness type load transfer. Here I have a lot of different options for how the transfer direction should be. Maybe only in X direction of the surface, in Y direction, or in both directions with stripes. Or the more exact thing would be the isotropic FEA option, but in our case I think the stripes are okay. I could remove some objects which should be not loaded. In our case it's okay. Can continue with okay, and can create here's this surface. The same I can do for big openings. For openings, I would have a second option, the option to create directly a load on the option with new opening load. Here I want to show both options. For the new opening load, I can use one value in X direction and can choose opening. Okay. Then automatically this load will be transferred to the lines around the opening. I can show also the load on the boundary lines. So for the load transfer surface, I can use the default or the basic surface load. With the same value in my case, and can choose the surfaces where it should be acting. Okay. Also for the load transfer load, I can show the distribution surface, what is acting on the separate lines. Here you see I have it's transferred to all loads in linear way in the stripes of Y and X directions. Okay, if we have everything defined, then we can start with calculation. Here I want to compute maybe one load case to take a look on the results. Okay. The calculation was done without any errors. That's good. So everything is okay. So now I want to show you the results of this inner walls, where we had used the thickness type shear wall, shear free wall. I want to select only this. Okay. So here I can see when I take a look on the internal forces, I can see that the shear forces are 0. Also the moments are 0. When I take a look on the axis system, then my nx is nearly 0. It's not exactly 0 because of the reason of is it could not be exact 0 in calculation. So there are small loads in X direction, but I have big forces in Y direction. Therefore, I have only loads transferred from the slab in the second floor to the slab to the third floor. That means this option or this thickness type is good when I have some masonry walls where I have maybe a concrete structure what a concrete structure what takes my shear forces and something else, and I want only have the self weight or a transferring from the loads from the upper slab to the slab downside, then I can use this thickness type shear free or this wall shear free. In case that the masonry wall should also acting for shear forces, then we should use this isotropic masonry or this orthotropic masonry. For this isotropic masonry material model, I can now take maybe a look here. Here we see that we have load transferring, we have stresses in X and Y direction. When I take a look maybe on this wall again, then we see that we have only tension forces in the defined limit. Tension forces in the defined limit, and the way pressure. So how could we interpret these results too? You could insert here again a result beam. With the result beam, we could use here a block with 1 meter, where we want to include objects, maybe only this one. Okay, I can create it's not important, but I create a new one. Stiffness, because the result beam does not have a stiffness. For the calculation, we have here 1000 to 380. Okay, and we can add it here. Then we have to recalculate it only because the lines are divided or integrated in the surfaces now. But this result beam have no stiffness for this calculation now. But now you have the possibility to take a look on member results. Here you can see the internal forces, maybe for the normal forces. Oh, sorry. For the normal forces or for the acting moments in this wall. Because we use this isotropic masonry, you could use now the results of this result beam for an additional design of the masonry surfaces too. So this would be all what I want to show you today. I want to say thank you for listening. I hope you enjoyed it, And I want to give back to Andreas.
Thank you, Ulrich, for your presentation. At the end, I have an additional hint for you. You can book our online courses. For example, the Rfem 6 Masterclass course. It's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with Rfem 6. Eurocode 3 for steel design. Eurocode 5 for the timber design. And there are also course packages available. For more information, just scan the QR codes in the middle, or you can click at the links at the bottom of the slides. You can download the slides from the same website where you can find the recording and models. And the next days you will get an email with a link to that page. And the email contains also your attendee certificate. Okay, that's for the moment all from my side. I thank you for your attention. Thanks again to Ulrich for the presentation. I wish you all a nice rest of the day. Bye-bye.